Well, hello. I've heard these were really good scopes. This is a Sencore SC61. Managed to find one on eBay for $40. Run me about $60 with the shipping. Had a bad volume, or not volume, but power switch. And other than that, all I had to do was give it a really good cleaning. And it sat on my bench because I didn't have any probes for it. So I ordered these ones off eBay. And this is the P6100, 100 megahertz. I believe I got these from Sencore. They're about $20 for a package of 2. And in my Sencore manual, there is a schematic for the probes that they use. These won't work direct because there are ×10 that go with the Sencore. So I could just turn the probe to the ×10 setting and it'd work fine. However, the Sencore comes with this nice little DC input voltage, and over here on each channel you can select the digital readout for DC volts. But I did not have the Sencore probe, so I go back on eBay. Cannot find any. So I ordered these probes from Sencore. This is the P6100, which is 100 megahertz. I think that's probably the max bandwidth for this scope. And I'm going to show you how I modified them to work with my Sencore SC61. So first up here we have the schematic of the P6100 probe. Has the ×10 switch in the probe itself. The other end with the BNC connector has a 100 ohm resistor, a 50 ohm resistor, and the 20 picofarad trimmer cap for compensation. Now this will only work if it's used for AC. The DC setup on the Sencore is slightly different. So this is what the Sencore looks like. You have your typical 9 meg input resistance, but then down on the DC side you have a 13.5 meg resistance. This feeds into the DC side at 1.5 mega ohm resistance. The AC side has a 1 mega ohm resistance. You'll notice there is no ×10 switch on these probes. So when I look at the schematic, I thought, well, I've got the 9 meg in the other probe. I can just add a 4.7 behind it to make a 13.5 meg for the DC side. So that's what I did. I got a 4.7 meg resistor and hooked it up. This is the schematic of what I came up with when I adapted it. Instead of having the DC side connected directly to the probe, I connected it to the end of the 9 meg and changed this to a 4.7, which technically should have worked correct. However, when it's hooked up to the AC side with the mega ohm resistance in there, it throws the DC voltages off. So I had to go back and redesign it. So this is what we're shooting for my Sencore probe. And now I will disassemble, and you can watch how I took this apart and made it the same as the Sencore original probe. You have the BNC end and the probe end. Probe end has the 9 meg ohm resistor with the 1 and ×10 switch on it. So to figure out how to get this apart, you can take this rubber end off like so. Slide it back. This is the compensation end. You slide that back, and there's your little circuit board. Now you have, you can see this, down here is a 50 ohm resistor, the 20 picofarad trimmer, and up here is a 100 ohm inline resistor. So to modify, I removed this resistor completely, left the 50 ohm and the compensation in. And we will need the 9 meg ohm resistor. And since I'm old, I always verify these. I especially dislike the blue ones because they're even harder to figure out with the color code than these are. However, you can get this handy little device off eBay for about $10 to measure the resistance. First one is installed. You leave the second leg unsoldered until you get the second resistor put on the same pad. The reason we have to do this way is because of the space limitations on the sleeve that slides over the trimmer. Okay, second resistor is soldered down. See if I can turn this so you can see how it's positioned. Very cramped quarters in there. Now the third resistor we're going to solder to the other end over here to make our DC lead. Okay, there's the third resistor soldered into place. And next we build our wire and banana plug for the DC plug-in. Now to do this part, I want to cut right here behind the blue ring on the first flexible edge of the cover. Now for the lead, let's see if I can find the one I built. I have about a 6-inch wire. Now this is a regular, let me get this out of here. This is a regular banana plug, but I just peeled the flexible fins off the end, and it fits right into the DC input on the Sencore. Okay, so we notched the rubber sleeve, and making sure we put the plug in the correct way, ran the lead through. It's going to hang out here. We're going to put a piece of heat shrink over it, and then trim the resistor and solder those together. So we got it soldered on there. You want to make sure your insulated heat shrink is on the wire and that both of them run through the sleeve. So now we'll heat shrink and reassemble, and I'll show you what it looks like when it's done. Then we'll take some voltage measurements. Now I don't know if you can see this, but there is a notch in the end of the sleeve there. I'll get my pointer here. Right there is the notch. So we're going to put the insulated wire through there, and then put the sleeve back over and the rubber cap, and we'll be done. This is what it looks like when it's all routed correctly, making sure there's no shorts, and we'll assemble. So this is what it looks like reassembled. We've got our mini banana plug. Now I don't particularly like these. It's one of my eBay mistakes. The screw is directly connected to the hot side, so I tend to put some heat shrink over the top of these. But I went ahead and ordered more banana plugs offline. I like the Panoma ones, but they're hard to find. But yeah, I don't like these screw together ones at all. Now insulated with some heat shrink, and we'll hook this up to the scope and see how it works. So we have the DC bench supply dialed in at 5.1 volts. Let's see if we can get it down to 1. 5 volts, connected to the probe. You want this on the 1x setting, since we already put a 9 meg inside the BNC connector. And we're hooked up to channel A. Gotta have the DC plugged in or it will not read. You do not have to have this on DC coupling. Now over here you want the DC volts button pushed, and right now we're just under 5 volts, so we're 0.04 of a volt off. Not too shabby, I would say. So my thought on this is using the little tester machine here, you can measure your 9 mega ohm resistors and find a pair to match up with the 4.7 mega ohm resistors to get the correct reading on your voltage. Might take a little playing, but you could get this highly accurate. Now another comment on this oscilloscope, took up quite a bit of space, but it does have quite a few features that I really came to appreciate later. One was, okay, you've got the voltmeter here, and over here you have push buttons for A and B channel. You can do peak to peak voltage if you're on AC, and you can do the frequency measurement. Now my tests on the frequency measurement, they'd only ran up to a little over 50 megahertz before the frequency counter crapped out. And over here you have delta measurements where you can set the start and stop of any waveform on the screen and do like a capture on it. This is one of the very first microprocessor controlled scopes, and didn't quite know what I was buying when I got it, but I really like this now because I can eliminate 3 of my test bench pieces all in one unit here. Actually 4 if you count the delta measurements.